So let's continue with the interconnections and contacts. We've stopped right before electromigration. So we're gonna continue with electromigration today. Okay, can you see the slide? All right. So electromigration is one of the reliability issues that we have in IC fabrication. So if you look at a wafer fab, for example, we normally have a fab support group which consists of many departments, including FA and reliability. FA is failure analysis, and reliability is another group, right? Apart from these two groups, we also have another departments like customer engineering, QA, and some other departments. So reliability is a huge issue that we have to look at after fabricating the IC. So we have to make sure that the device works well as desired. And if you talk about electromigration, it's one of the reliability issues that we have in the device. Okay, what is electromigration? We're going to play a video later on, but let me just go through the definition before we play the video on YouTube. So it's the transport of material caused by movement of ions in the conductor due to momentum transfer between conducting electrons and diffusing metal atoms. So we're going to have movement of atoms in conductor in our metal contacts due to the flow of electrons. So that's what it essentially means. So due to the flow of current, which consists of electrons as the carriers, due to momentum transfer during the transport, we have movement of atoms off the conductor, which could lead to reliability issue. Okay, so maksudnya elektron yang ada dalam conductor dia akan they can shift the position of the metal atoms. Then eventually we don't have what you call the original conductor punya structure. So you might have some shift, you might have some breakage in the conductor. Okay, so let me just play this YouTube video and share with you. I've also uploaded this particular video on eLearn. Hold on, yeah, let me share first. Okay, hold on, let me share the page first. It's a bit slow here. Right, can you see the YouTube page? Okay, good. So let me just play this electromigration in a gold nanowire. So this is a gold nanowire that you can see on the page. So let me just zoom it to full screen. Okay, and play. It's only 29 seconds. So let's see what happens to the contacts as the current passes through. Agak slow, agak slow. Okay, nampak kan apa jadi tu? So you can see the breakage of the contact. Let me just replay. So you can see the gold contacts or the gold nanowires shrinking sikit kat tengah tu. Then eventually it breaks. It breaks in the middle. Okay. So that's one of the what we call observation that we can see during electromigration. So you can find many more examples online to show electromigration. Let me share the slides again. Sorry. All right, so let's get back to the slides. Sorry. Okay, so so when you have your contacts or your wires break in the final device, so you're gonna have reliability issue. Maksudnya device itu dah tak reliable lah. So it will not function as intended already because the extraction of the carriers will not be the way it's supposed to be. So that's due to electromigration. So let's look at electromigration in more details. So it's due to high current density causes voids. So it's due to high current density passing through the your wires, for example. So in this case, you can see two SEM images. The first one on the left, you can see the wire breaks in the middle due to electromigration. So bila jadi macam ni, what happens is it's going to be open circuit. So it's going to be open circuit. Maksudnya you punya, if your conduction is supposed to be going through this particular wire or all these wires, then you're not going to have your current passing through the middle one because it breaks in the middle due to electromigration. So another one on the right, you can see another example as well. So the wire breaks in the middle, causing open circuit to the device. Okay. So just imagine if you have only one wire running through the device, so you're not going to have any connection at all because it breaks in the middle. Okay. So the atas you can see electromigration is due to momentum transfer from the electrons moving in a wire. So electrons moving are causing current to flow on the opposite direction. So the movement of the electron and the momentum transfer from the electron move the copper atoms or the aluminum atoms or whatever atom that you have that makes your contact, right? So it is easily happens when you have a high current density through your wires. So if you have a higher current density traveling through the wires, so you're gonna experience more momentum transfer in the wire, so then leading to more possibility of electromigration. So in this case, it causes voids or breakage. For example, dari lubang ni in the interconnection. Okay, so this is also called the momentum transfer from the electron in the current carrying conductor is also called electron wind. Angin electron, electron wind causes movement of metal atoms. Because if you look at the the weight, also the mass of the electron is very, very small, right? So you barely feel the mass anyway, but that's why we call it electron wind. But then the effect is quite tremendous to the atoms of the wire. Okay, so current density is given by J J is given by I over A. So current divided by the area of the conductor or of the wire. So if you have, for example, kalau you tengok dalam example tadi, where you have a shrinking area of the gold nanowire as the electromigration evolve or develops, so you're going to have less and less or smaller and smaller areas of your wires, right? Your wires. So kalau you punya wire is getting smaller along the process, maksudnya if you pass through the very same amount of current over smaller and smaller A or shrinking A, and then over time during electromigration evolution, then you're gonna pass through effectively higher electron density through the conductors. Okay, sebab over time you akan nampak atoms by atoms move, so you technically reduce the area of your conductor already because you are left with smaller and smaller wires area, right? So you can see an example of the calculation down here. J is equal to I over A. So if you're talking about 1 ampere of current passing through 1 micron, for example, if your area is 1 micron squared of the conductor, kalau you punya conductor bulat, then what pi r squared, right? Pi r squared equals to 1 micron squared, for example. Then that's going to be giving you about 1 mega amp per cm squared. So such a high current density. Okay, so you won't have this electromigration instantly. So maybe you won't see the effect in like 1 hour, 2 hours. Maybe it takes days or weeks or years depending on the condition of the conductor, right? So there's no fixed duration of electromigration, but rather it evolves over time. So how fast or how long along the way do you develop the electromigration really depends on the parameters that you have for the wires, for the current, and for the atoms that makes up the conductors and so on and so forth, right? So that's electromigration. This electromigration problem can be modeled by Black's equation. So this one is the one that I added on the slide. If you compare to the previous slide, so it's already uploaded on Elon. So it's called Black equation. So essentially it's a mathematical model for the mean time to failure, or we call it MTF, or you can also find references which say MTTF, mean time to failure, of a semiconductor circuit due to electromigration problem. So essentially it means how long do you need before your wire fails, for example, right? So before your semiconductor fails, because your semiconductor relies on the interconnection as well. So it's not the failure of the wire alone, but rather the failure of the whole semiconductor, because you won't have a fully functional device without your wires or your interconnections, right? So it's a mathematical model for the mean time to failure. You can also write MTTF, right? So it's not only MTF. So if you write MTF, it's fine. If you write MTTF, it's equally fine. Mean time to failure. So kalau you join Fab, nanti you're gonna encounter this word, but not only for electromigration, it's also applied for equipment uptime. So kalau you're the equipment engineer in particular, then you're gonna need to monitor one metric, many metrics actually, including mean time to failure. So how long can your equipment run before it fails for another problem? So the longer the time, the higher value your the higher value of your MTTF. So that means longer time it takes before it actually fails. So that means you have a lot of uptime rather than your downtime. Okay. Ada banyak lagi. If you talk about equipment, then we are also monitoring MTBI, mean time between interruption. So the punya calculation is slightly different, but essentially it monitors the same thing, mean time between interruption. Ataupun MTBF, mean time between failure. Right? Kalau you are process equipment engineer, for example, And these are among the things that you're going to be working with or monitoring day in and day out, right? So Black's equation, copper added to aluminum. So if you're looking at the traditional conductor, they are all based on aluminum. So in order to reduce probability of electromigration in aluminum wires, you can also add copper into the aluminum to improve the lifetime. So that means you can prolong the life of your wires or of your interconnects by adding copper by about 4% into aluminum and 1% of silicon into aluminum as well. So this will prolong the lifetime of your aluminum wire, for example. So if you look at the chart on the left, figure 7.8, you can see cumulative failures on the y-axis in percentage, and then on the x-axis is the time to failure, or MTTF if you like, mean time to failure. So if you use Al copper on the left hand side, right? So, or if you mix a little bit of copper into aluminum, so this would be your cumulative failure trend. Okay, so your trend, you can see here the trend is like this, it's slanted like that, but it corresponds to a relatively short value of your MTTF on the x-axis. Okay, ataupun mean time to failure you is still low. So maksudnya if you compare to pure aluminum, then it should be further left. It should be on the further left side of aluminum copper. Okay, so aluminum should be on the far left, but it's not here in the graph. Then aluminum copper comes in slightly shifted to the right because of the addition of copper, which prolongs the lifetime or reduces the electromigration. And if you switch to copper completely, for example, then your MTTF is going to increase. It's going to move to the right. So the lifetime is more or less 10 times better than ALCU control, ALCU interconnects, right? So the equation of the Black equation is given by this MTTF or MTF proportional to 1 over J squared exponential activation energy. J is your current density, EA is your activation energy, over Boltzmann constant times the temperature at which your interconnects operate in the device. All right, so MTF or MTTF is the mean time to failure. So the reason for the longer lifetime of the copper is due to heavier metals of the copper, and it has a lower activation energy as well. So which prolongs the MTTF of your interconnects. Okay. So this is silicide. Silicide of noble and refractory metals can be used to reduce sheet resistance of polysilicon and diffuse interconnections. So we will encounter, or you will encounter later on your device, sheet resistance problem. So either it's on the IC or solar cells or LEDs or some other devices. Sheet resistance is one of the most important parameters that you have to know. So silicide, if you talk about silicon, then silicide is the one of the main parameters that's crucial for you to ensure that you have low sheet resistance in the device. Okay, so you can look at this diagram up here. Your silicide is on top of your polysilicon before it is connected to metal. Okay, so provide shunting layer in parallel with the original interconnection. So this is among the silicide that we have that we can choose from. So properties of silicide of interest. So we have range of different silicide from noble and refractory metals. We have cobalt, silicide, hafnium, molybdenum, nickel, palladium, platinum, tantalum, titanium, zirconium, tungsten, all silicide, right? So they can be produced by various methods: metal and polysilicon, co-sputtered alloy. Generally, they are co-sputtered alloy. So to be able to get a good alloying between those two materials, cobalt and silicon, for example, or hafnium and silicon, you need to work with the right sintering temperature so that you form a good alloy. So the temperature ranges from 900 to about 1000. For most of them, one is slightly lower. Palladium, for example, is slightly lower. Platinum is slightly lower, 600 to 800. But the rest are in the region of 900 to 1000 degrees C. Lowest binary temperature, you can always get these values on the binary on the phase diagram of the binary compound. So you've done your phase diagram experiment last time, remember during your second year, you buat phase diagram kan? Ingat lagi tak? Thin lab phase diagram. Ada ingat? Your second year last time, I was the person in charge. Fazira, ingat lagi Fazira? I think you did with me as well last time. Go, Fazira, ingat lagi tak? Yes, right? Yeah, exactly. Thermocouple thing, where I think most of the groups had to extend to at least 3 sessions to get the data done. Right? This time around, your junior, your second year student, they are given the data because they are not allowed to be on campus. So no student on campus. So the students are supplied with the data to do the plotting and analysis. They don't really have to do the experiments, right? This time around. Right, specific resistivity varies depending on what sort of silicides are you working with. Right, this is silicide as well. Another example is self-aligned silicide on silicon and polysilicon. Is also called salicide, right? So it's not only silicide but rather salicide. So you have deposit oxide and polysilicon, N plus layer here, oxide spacer. Then you have eventually for the last one here, you have a self-aligned metal silicide, because when you say it's self-aligned, so it sits accurately on the polysilicon. So it has to be aligned in the printing process, in the lithography process. So we call it silicide. If you talk about general silicide blanket deposition, then it's silicide. Kalau you perlu align dia, then you pattern, then it's called salicide. Right, this is another example in bipolar and MOS devices. So from here you can see that there is no one specific arrangement of the device configuration. It ranges so widely. So in this particular case, you see something different. The structures are slightly different. If you look at the previous one, it's also different. So the one that we've learned in the beginning is like a very simple structure of the MOSFET, where you have gate on your gate aux, and you have the body, and then you have source drain, and that's it. And here you see like N plus, P plus, self-align, ALCU contacts, titanium tungsten, palladium silicide. Yeah, so it really depends on which particular device you're working on. So there is no generic structure. Okay. So interconnects leaf-off process is one of the main processes as well, even though it's not labeled as one main process like the way we call lithography, etching, implant, thin film deposition, thermal oxide. It's not, but it's also a process. Okay, we normally do it when we work with metal contacts, so we call it a leaf-off process. Okay, leaf-off. So what if leaf-off process? So let's look at the one on the left, where we call it subtractive etching. So we deposit a metal layer on the wafer, and then we deposit, we spin the resist and pattern the resist by CD process, and then we etch the metal layer on the sides, left hand side and right hand side, and then we strip off the resist. So then you have your contact like this. Okay, so you are left with this aluminum, for example, pattern on top of your wafer. So that's called subtractive etching process. Okay, maksudnya you etch lah. Effectively you etch the structure. You start blanket, and then you etch until you get the final structure that you want. On the other hand, on the B side, on the right hand side, we call it additive metal lift off, where you pattern the resist on the left hand side and on the right hand side before the deposition of your metal. So you tengok ni terbalik So you pattern the resist first, then only you deposit the metal. Kalau tadi proses A kita blanket deposition of the metal first, then only we pattern. It can be done both ways, right? So in this case for B, you pattern the resist, and then you have the opening in between. Then you deposit your metal layer blanket, but then the one on the left hand side and right hand side are going to sit on the on the resist, of course, because you already have the resist there. So this one metal as well, semua tu metal. It's just that they sit at different levels because you already have your pattern resist on the left and on the right. Technically, they are blanket deposition. So blanket deposition. Then you leave off the resist. Bila you leave off the resist, then the metal sitting on the resist will also be lifted off. Okay, will also be lifted off, right? So then you're going to end up with the very same structure on the wafer. So if you compare the one on the left and the one on the right, so they are exactly equal, right? So they're the same, but they can be produced by two different routes. So the one is subtractive etching, where you do metal deposition blanket, then only pattern the resist, and then you remove the contacts in the unwanted region, right? On the other hand, in the figure B, we pattern the resist, we blanket deposition the aluminium, for example, and then we leave off the resist, and you're going to be left with the metal or aluminium on the wafer. So this is called leave off process. Multi-level metallization. So we have covered last time about metal 1 until metal 8, or in fact more than that. So that's what it means by multi-level metallization, more or less. So we've covered during process integration as well. So two-level metal processes, it can be more than that. Silicon dioxide, polyimide, nitride, dielectrics can be used in between. So vias form to connect between metal layers. So we've seen the insulation between metal 1 and 2 by IMD1 last time, IMD2, 3, 4, 5, so on and so forth until the very end, until the top metal and passivation and the pad, bond pad for the external connection. So vias can be filled to improve planarization. For example, in our case, we learned about tungsten deposition and then tungsten CMP, tungsten dep, then with tungsten CMP, and then it's ready for the next metal patterning, right? Metal patterning. So sama ya, cuma it looks, the schematics look different, but essentially the points are the same. We're almost done, really. Multi-level metallization. So this is another cross-section example. So I've given to you a couple of examples already in our group, in our WhatsApp group. You can see here multi-level aluminium metallization with tungsten plugs. So you've learned about the plugs when we learned about process integration. So this is like, for example, if you revisit your process integration notes, then you can relate this as perhaps metal 1 will be there, then your plug will be in between, then metal 2 here, then metal 3 here, right? So this one, I'm not sure the exact layers. So this one is perhaps your another metal layer, right? Maybe this one is another metal layer as well, but you don't see the interconnection in this particular picture. Maybe it's slightly outside. I don't see the interconnects here. I don't see the plugs connecting the metal layers. I believe it could be outside the captured figure, right? But normally what you see from SEM, if you see of the same color, so more or less, or most likely they are from the same material. For example, metal 1, metal 2 ni mungkin sama, composition slightly different, but they look the same on the SEM image, right? So the contrast is similar, so more or less they should be similar material. Okay. Example of multi-level aluminum metallization with tungsten plugs via tungsten via plugs. So tungsten via yang Syah tanya hari tu. So tungsten in the via. So you pattern the via, then you deposit tungsten, you CMP the tungsten, and then you're ready for your next metal layers. Then you do the CMP. Planarity achieved through CMP. So remember the rule of CMP is to planarize the deposited surface so that you don't have bumps before your next lithography process, or else you'll be out of focus. Your DOF, your whatever parameters that you have in the lithography process, right? Another example of copper interconnect, you can just click this link on Wiki. So this is actually from Wiki. So this is how it looks like. So it's very neat here, neat interconnections, very nice, very beautiful. So it's copper on your chips, right? So replacing aluminum wiring in chips had been thought by most to be impossible, because last time the traditional circuitries used aluminum wiring. So people thought it was impossible to replace aluminum with some other metals back then. So for a number of technical reasons, you can look for these reasons if you want to. However, IBM team overcame those technical problems, bringing copper wires into production quickly, giving an immediate boost to chip performance, right? So you can change the process to use copper instead of aluminum. During my time last time in Sotera, 2009, I think back in 2007, 2008, Silterra started C13 process. So C13 is based on copper, so which was transferred. The technology was transferred from IMEC in Belgium. So back then there were quite a number of engineers who went to IMEC in Belgium for training for like 6 months, 9 months, some 3 months, to learn about the C13 process, C13 technologies based on copper. And Silterra had never run copper before that, and brought back the technology to start development lots, development wafers. So the challenging thing about copper is you cannot contaminate your silicon with copper. We've learned last time in 386 that copper, C13 is copper based. Copper is a lifetime killer in the silicon. Okay, copper is a lifetime killer. Kita belajar ni waktu kita belajar, I think defects or something, recombination code, lifetime killer in silicon. So if you have copper in your device, so it's going to kill your device instantly, right? Then how come you want to use copper in the interconnects, but then you don't want to use it, you want to make sure that they are not in the device, but physically they are on the device, right? So macam tak make sense, huh? It's a bit counterintuitive, right? Counterintuitive, because you don't want it to be in the device, but yet you use it on the device as your interconnects. So there are a few procedures that we had to do back then. We call it contamination, a decontamination procedure. So we didn't have enough number of equipments to run copper and non-copper specifically. So we had to mix copper and non-copper on the very same equipment, but at different time, of course. So what had to be done back then was we had to allocate a couple of hours per day to run copper lots, copper-based lots, and some other times of the day to run none other copper lots. And copper lots or copper wafers was placed in green pot yang kita angkat tu, yang operator angkat is green color. Dia punya code yang kita pakai green color. Green means copper, right? And other pots, the white pot, the transparent pot, are for non-copper process. So you're not supposed to have at the same time running green pots and transparent pots at the same time, because your copper in the green pots, in the green wafers, are going to contaminate your non-copper lots. So we had to allocate a different time. And when I was an EE back then, equipment engineer, after running copper lot, we had to stop the equipment decontaminate the whole equipment, doing the cleaning for like 1-2 hours to make sure that every single module in the CAD process, so hot plate, cool plate, coater, developer, WE, EBR, what else? Robot arms for all the regions need to be wiped cleanly, and then we had to run hundreds of test wafers before we release to mass production. We ran hundreds of test wafers through the system after the decontamination process, and then we had to go for TXRF measurement. So it's one of the characterizations available in the fab. Total X-ray fluorescence. So it will detect metal contaminants on the wafer. Kalau you ada contaminant on the wafer more than certain levels, out of the spec or beyond the spec limit, then you cannot release the equipment to run mass production of non-copper lots. Then you have to go back to the equipment, rewipe again, find out the root cause, rerun the test wafers, redo the TSRF measurement, make sure that the level is within the spec limit. If it's within the spec limit, then only can run for mass production to run non-copper lots. So that was one of the big challenges when you don't have enough equipment to run just copper and non-copper, right? So these, however, you know that copper interconnects can boost the chip performance, but you don't have enough equipment to do so. What you have to do is you have to allocate time and have procedures followed by everyone to make sure that there's no cross-contamination of copper into non-copper. The moment you have contamination, gone. Your wafers are gone, right? It's going to be scrapped. Okay, so copper interconnects, how do they look like? How's the process look like? Okay, copper deposited using standard plating processes adapted to microelectronics. Okay, seed layer deposited, mask layer deposited, and pattern. You can plate the copper, you can pattern the copper, then you can remove the masking, then you're left with the plated copper interconnects, right? So another process called Damascene process. So this is one of the rooms in Soltera, if I can recall correctly, Damascene room. So Damascene, it belongs to Damascene process, used to obtain highly planar surface. So this is how it looks like. Okay, dielectric layer insulator deposited and patterned. So you have dielectric there. It's patterned on the left and on the right hand side of the wafer, and then your seed layer is deposited on within the hole there, within the open area, and then you do the copper plating in between in the open areas, and then you close it by, you wrap it up by CMP process to make sure that your copper plate or your copper electrode is planarized. So that is copper Damascene process. So interconnection for copper dual Damascene process. You can also do dual Damascene process instead of a single Damascene. Okay, dual Damascene process flow. This is how it looks like. So you have substrate here, copper layer. You have insulator. Then you have nitride as your ash top, another insulator. Then you have to have the resist on, and then you pattern the metal. You have the resist on there, and then you do the deposition of the layer on the insulator there. Okay, another example of the interconnects. This one is copper on the left. So your device is at the bottom of the FreeSAM cross section. So your device is down there. So if you notice, your transistor is always down, and the rest are all interconnects. Okay, kalau you ada rumah kondo, then your device is dekat dia punya parking, and the rest are all interconnects. Okay. So plugs, then you have metal 1, you have ALCU inner interconnections, then you have metal 2 plugs, metal 3 plugs, metal 4, metal 5, then you have Damascene at the back end of the process. Then you have a couple of nitride stops, silicon nitride stop, this one. Ash stop nitride, you have a couple of this, so you can see this on the SAM cross section here. Right, so you have Damascene process, copper deposition, and then passivation, then done. So on the right hand side, you have the cross section as well. So of the dual damascene copper interconnects, so you can see the neatness of the interconnects formed there. Cantik ya nampak? So you can see the metal layer here, the plugs in between, metal plugs, metal plugs, metal plugs, metal plugs, metal plugs, until the top metal. Okay, I don't know how many metal layers are all together. Maybe 1, 2, 3, 4, 5, 6, 7 maybe. I don't know what's going on up there, but it looks like another layer as well. Yeah, that's it. So we're done with the interconnects and contacts. We are also done with the whole course topics. All right, how are you going so far? Do you have any questions for the interconnects? 2:42, early today. Ada soalan ke? Okay ke so far? Tak ada soalan? Let me just recap our course synopsis before we end. Tomorrow I'm going to give you a special lecture on process flow for solar cell, silicon solar cell. Ya, saya buka slides. Let me share with you. All right. Ah, you have another test on 20th? Same time, is it? Fazira, same time, yeah? 5 p.m. Open book as well? How long? How long is the test?
The doctor did not decide yet, more or less.
Oh, subject mana? Subject mana tu?
Minor.
Ah, okay. All right. If not, then usually subject tu test berapa lama? Do you have any idea?
Base Dr. cakap hari tu dia nak plan 2 jam. More
Okay.
2 jam.
So kalau 2 jam, okay good. Is it okay? Mine is 24 hours, right? So
Okay lah.
yeah, good. I don't have to reschedule. Kalau tidak, nanti I might affect some other schedule as well. So,
Okay lah.
so let's stick to our date, 20th. So let me recap using our. Let me share with you the slide again. Let's recap the content that you have covered so far. Oops. Okay, can you see the slides now? The day one slides. Can you see? Okay, good. So let's just recap before we finish officially. All right, so as I said in our very first lecture, at the end of this course, you should be able to, so we're not able to do one of the main things in this subject, unfortunately. So you should be able to analyze processes involved in fabrication of wafer and semiconductor devices. So we've gone through all the materials and we've discussed a couple of case studies, a couple of issues, and we've gone through a bit of calculation as well. So you should be able by now to analyze processes involved in terms of the difference, the properties. What if you use subtractive etching or additive etching just now? What if you use isotropic etching or RIE first, the one that we did on our case study last time, a couple of approaches where we discussed about double patterning and also the isotropic plasma etching process, right? So you should be able to analyze the difference and the properties and how does it look like on the wafer, what's the impact, so what should you expect as the results. And then fabricate semiconductor devices. Obviously you cannot do this because of the COVID, so you're not back. So I planned this after you came back on the 7th of December, but unfortunately the situation prolongs and we may end up with another PKP as well, I heard, maybe. So you don't get to do your fabrication yourself. This is one of the things that I think is missing, but we have no choice. We have no choice because you're not here to do the fabrication. If you get to do this, then you have some experiences of doing some process. So you may not be able to do all processes at once because it's just going to be so long. Knowing that the lab booking and COVID and postgrads, so on and so forth. However, you get to do at least one process for a group. So at least one group gets to do sputtering, for example. Another group gets to do etching. Another one gets to do oxidation, maybe, or doping, and then do a little bit of characterizations as a result of your process. So I normally advise students to put this on their resumes as mini project, even though it takes like barely 1 month, three weeks perhaps at most. So it is usually strong enough to be justified as one of your mini project, as long as you know how to explain to the interviewers about the project that you've done and what you learned from the project, because it's not going to involve the technical part of the fabrication only, but rather the teamwork, the planning, taking turns and stuff like that, leadership. So it's all embedded in the fabrication work, but we don't get a chance to do that, unfortunately, this round. Okay. However, you still can do the third one, presentation of your fabrication processes in the group. So usually when I do my mini project on the number 2, fabrication, so you will end up presenting your processing and your results to me in the class and to the other group as well. And we're gonna have Q&A sessions based on your result, just like a mini Viva session based on your results and the process and the parameters that you use for your fabrication. But this time around, you are assigned to do fabrication processes of your device, FinFET or solar cell or power device or LED, which is done by the literature reading, more or less. Okay, literature reading and some referencing to companies maybe as well. So you get to do this. So you get to do the presentation, even though you are not around to do presentation face to face. We can only do that by video. But anyway, you will still be assessed by the clarity of your presentation as well, and the confidence of your presentation as well. So even though it's video based, with some limitation, you can still be assessed as the original plan, right? And then the final one is organize information related to semiconductor fabrication processes. You manage to do this by your assignment 1, assignment 2, and then you can also do this. You can also learn this by your presentation as well, because to be able to get information on the fabrication processes of your device, then you need to get some information about the device, about the processes, put them together in the order that I have instructed in the presentation worksheet. So what you have to include first, what's next. So it's all within the organization of the information related to the presentation. So we only miss number 2 in this case, right? But the rest are all achieved. Okay. Yep. This is all the items as well, same. So we've also changed our coursework from 50-50 last time, 50 coursework, 50 exam as intended originally. We just scale up this coursework to 100%. So your test is going to contribute 40%, 20 times 2, 20% times 2. Assignment is going to be 15 times 2, 30%. So your presentation is going to give you 30% as well. So altogether, 100%. So we have covered when we started last time, introduction to semiconductor fabrication. You have learned also about growth of silicon ingot. So you now know how do you grow the ingot. So what are the limitations? What are the processes involved? How do you improve the ingot fabrication? How do we prepare silicon wafer? And what are the properties of silicon wafers that we are looking for in order to be accepted as a good standard for fabrication? And then we've gone through introduction to clean room. You know the do's and the don'ts in a clean room with different classes. You know that perspiration is one of the main problems or main contributing factors to contamination problem in a clean room, right? Our walking, our movement, handling of the wafers, and cosmetics and perfumes and stuff like that, right? Then we've discussed about the very first process, thermal oxidation. To do pet ox, field ox, you can use dry ox, you can use wet ox, depending. You can even mix dry and wet according to depending on the processes that you want to get, the qualities you want to get on your device. Then we've covered CED process in lithography. We learn about coating, we learn about exposure, we learn about development process, and we also learn about metrology, which covers FSAM, visual inspection, overlay to align your current layer to the underlying layers to make sure that they are not off the track in terms of X, Y, and theta alignment. We've learned about etching, we've learned about dry, we've learned about wet etching. So you even have questions to answer on the etching, on the wet etch, I think. Yeah, wet etching, right? In order to produce silicon nanowires. So you've gone through diffusion in order to learn how do you actually dope your sample, how do you form a junction, how do you get P plus, P minus, or intrinsic. We learn about intrinsic as well if you don't dope your wafer at all. And how do you end up characterizing the junction that you have formed in the diffusion process? So you've covered another method of doing diffusion, which is by another method of doping by doing ion implantation, where you can actually embed the junction inside the silicon. You can have a better control. However, it comes at a higher cost. We've learned about film deposition by PVD, by E-beam evaporation, by thermal evaporation, by sputtering, DC and RF. And you've also learned various methods of CVD, chemical vapor depositions, in order to deposit different layers with different properties. And then we learned about process integration from day one of the processing until you get to the surface preservation layer and the bond pad. And then today we finish interconnection and contacts, and it's actually part of bonding and packaging, but I don't cover the packaging intensively, right? It's part of this as well, actually. So we've covered what sort of contacts and interconnects and what are the issues on the interconnects that we have in the wafer fabrication. Okay. And then there will not be any review class, but because there is no final exam, and you won't have assessment which covers from day one until the very end. Rather, we splitted the assessment into test 1 and test 2 and others. So you have already been assessed on test 1, so that's over pretty much. But don't make sure that the knowledge is not over, okay? The assessment is over. So you are now going to be assessed in your test 2, where it's going to cover from etching, right? If I'm not mistaken, etching until the very end of the topics in this course. Okay, so that's going to be on the 20th of January, as we agreed. So tomorrow I'm going to give you the special lecture on silicon solar cell, and then from there you can also see how the processes on silicon solar cell relate to the IC fabrication. You can see that it's a lot simpler to do fabrication of silicon solar cell as a device in comparison to IC fabrication. So it's like comparing 3 months of processing versus one day of processing to be able to finish your product. Okay, so that's all from me for today. Is there any questions? Tak ada?
Doktor, untuk presentation memang kena letak video macam biasa kan muka kita tu?
Yes. Nanti okay, I told you to appoint one group leader. Nanti you just upload you punya video dekat Padlet. Okay, kalau let's say you punya video doesn't exceed the size of Padlet, you can just upload dalam eLearn, then tell me, then I will save your video and upload as a video punya note lah. Sebab kalau you upload as assessment, then nobody else can see, right? Only you and me. Then I'll save that video and display as one of the course punya notes lah macam saya buat sebelum ni. Then everyone can see. Then kalau you nak save some of the group punya video accordingly for your future reference, go entirely up to you. Because some files may not fit on Padlet, as we saw last time, and some other files may fit. Okay. Anyway, you try on Padlet first. Kalau tak dapat, you just let me know. Then you just upload on eLearn. Then I'll get to the file and save, and upload on the eLearn for public. Okay, Shah.
Okay, Doktor.
All right. Any other question? Ada? Right. Then I'll see you tomorrow for our very final class. Okay. Then you are left with your assignment, presentation, and test. Then we only meet on the day of the test, but virtually lah, kita tak meet pun kan. So tomorrow will be the last day. For tomorrow, sebelum kita habis kelas, I want you to turn on your video. Kita capture satu gambar kelas before the end of the session, okay? As a memory, right? So selalunya saya ambil gambar kelas sebelum habis kelas. But this time around, it's all blacked out, grayed out. You can only see your names. So one for memory for this batch. Sebab selepas ni mungkin dah tak ada kelas kan? Unless you want to stay and take elective for your 4th year instead of the internship. Yes, memory class in COVID situation. You're gonna remember this for life. Okay. All right, so I'll see you tomorrow then. Bye-bye. Assalamualaikum. Take care. So get ready for the picture session tomorrow. Okay. Bye-bye. Assalamualaikum.